Okay, I guess we can start. So welcome to the session 4. Today we have 4 presentations all coming from the United States. The first one is going to be from MLight about in-band network telemetry. The second and fourth are from ESNet by Richard and Miriam about DPDK, Kafka, telemetry, data, and so on, and S-flow monitoring. And the third one is coming from the Indiana University. So Geronimo, please start. The floor is yours. And as in previous sessions, I will inform you if there is a need to speed up before the end of the presentation.
Perfect. Thank you. Good morning, everyone. Geronimo Bezerra from Florida International University. The goal of this presentation is to just share a little bit of what we're doing in this side of the ocean with INT. It's very good that Mauro introduced a lot of things, a lot of context about INT, so I'm going to skip most of the description. But basically, INT adds metadata to every packet across the network. The metadata is exported directly from the data plane, meaning that there is no performance issues for the network devices, which translates into being able to track or monitor or evaluate every single packet line rate. And I know that there's being said a lot of metadata in INT, so I wanted to provide an example of what is exactly that MLight is using from the INT domain. So we're tracking for every packet the ingress port ID, egress port ID, ingress timestamp, egress timestamp, the QID, and the Q occupancy.
Ja sam se malo ranije javio. Samo sam teo da prokomentarišem ovo za mreže 2. Tačno je, ove godine imamo mnogo više studenta jer su došle ove...
I think that some microphone has not been muted. Please mute your microphone if you're not speaking.
Yeah, that was not me. So there was a little bit of conflict. So again, the last bullet is the metadata that MLight is using, just as an example from these INT domain. So let me introduce a little bit of MLight. MLight is a National Science Foundation project that aims to connect, enables collaboration between US and Latin America partners, and also now Africa. It's a collaboration that extends to a number of NRENs in Latin America and Africa. It has currently 680 gigabits per second of upstream capacity between the US and Latin America, and 100 gigabits per second to Africa. It's a production SDN network since 2014. It has multiple points of presence. And the reason why we're deploying INT is the Vera Rubin Observatory. So it's a massive telescope being built in Chile. I have references at the end of the slides. I'm not going to go into the details of what the telescope is, but this telescope is going to leverage the MLight network, and it has a very strict SLA. So this is the motivation for INT. So this is the use case, the Vera Rubin use case. So every 27 seconds throughout the night, the telescope that is in Chile will send, we'll take a picture, there's 6.4 gigabytes, we'll process that picture, we'll generate the transient alerts of that picture, and then we'll send the whole package, that's picture plus transient alerts, to the archive site in the US. But from this 27-second time frame, only 5 seconds are available for data transmission. And this data is not going to be alone in the network. So we'll have, for the Vera Rubin itself, we have multiple traffic profiles. We have database synchronization. We have the telescope control. Also, the community uses internet traffic. There's everything that is also happening in the network, meaning that we need full visibility. We need full network visibility to mitigate any issues in real time, because the mean time to recover and the mean time between failures, according to the Vera Rubin SLA, is very strict. So we cannot we cannot keep missing multiple 5-second time frames just because there's a packet loss or something that is happening. So this led to a project that we called MLight INT, is also funded by NSF, the National Science Foundation. The goal of that project was to start deploying those P4 INT capable switches in multiple parts of our network in the US and Latin America. Most of pretty much covering the whole path that the telescope is going to use. And some of those sites we're going to have INT collectors, so those would be the nodes receiving the telemetry. And then we have to come up with the methodology to how to collect, how to export, how to process, and how to upload that information into our SDN controller to make sure that that network controller has a visibility and can make changes according to the current status of the network. So what can we do with with INT at MLite today? The main thing is, as was said before, Yatish also touched on this. With INT, we have the capability of selecting the traffic that we want to monitor. So we don't want to have visibility of the Netflix performance or Facebook performance. We're more interested in big data applications and the applications that have some sort of SLA. One of the things that we can do with the INT is that we can track the path that was taken by that packet in real time, including the egress interface. We can also see which link aggregation port members were used. So we create like a proof of trend. So we can guarantee that that packet flew through that link at that specific time frame. So this enables us to keep track of those changes, meaning that we can monitor the link flaps more effectively, and we can identify issues with the link aggregation hashing algorithms. We can monitor the delay introduced by each network hop in the path, which is very good to detect microbursts and high key utilization. We can monitor all the interface queues and then guarantee that the QoS policy in place is being correctly applied. So this is very important. And because INT, the way how INT data is exported also includes the user metadata, which is the TCP IP header, we can also correlate with events that the user see. So if the user see, like, let's say, a poor performance for a TCP data transfer, we also see that because we also have access to the TCP IP header. But now we have the INT, so we can try to pinpoint what the reason for the poor performance, if any, exists. So this is the main thing. It's not just a number of counters that we're collecting to see in a stateless approach if the network is behaving properly, but we also can correlate with the user data and make sure that the users are getting what they are supposed to get. So this is the first application. We presented this 2019. This is called Qtop. It's pretty much a queue occupancy monitor. So it gives us the flexibility of seeing all the queues of all the interfaces of all the switches of our topology. So we can monitor the number of cells or the amount of memory that is being used. We can monitor how the hop delay. For example, the one on the body, you see that for those queues, you have 941 nanoseconds, 1088 nanoseconds. And then you can see in red an example of, oh, it looks like there's an issue with the no flow switch 3, port 4, and the Q0, because now it's red and the hop delay, instead of being 1,000 nanoseconds, now it's 10,000 nanoseconds. So there's a clear indication that there's a possible bottleneck on that port. When we add the Qtop, when we connect Qtop with InfluxDB and Grafana, that's what the kind of visualization that it leads to us. Everyone talked somehow about Grafana or InfluxDB, so I'm not gonna get into those details. So you can see here that I have two vertical red bars. To the left of that bar, we have at the beginning of the data transfer that we did in TCP, and this is a couple minutes data transfer. So you see that we have a more stable kind of adjustment performance, and then to the right side you have UDP that doesn't like sharing, and it has a clear behavior. So the reason we're doing this is because we want to start using this to understand to ourselves, teach ourselves first is what we're supposed to see, because we never had the kind of information the INT provides before. So now we're in this learning phase that we have to first learn, and in the future we want to do machine learning, so we need to teach those machines, so we need to know what to teach them. So the first challenge that we saw with this project was receiving that data. If we have 100 gig data flow that has a packet of 9,000 bytes, that leads to 1.5 million packets per second. We have 6 to 10 switches between Chile and US that each report has 200 bytes to 220 bytes. And every user packet creates a telemetry report. So we're talking about 1.4 million packets per second of telemetry. And because of the size of the telemetry, we're talking about 4.5 gigabits per second. This is a single flow. There is no hashing, meaning that it always goes to the same queue on the NIC. It goes to the same CPU core on the server, means that the clock is very important. And then you have to do the pass to receive all that data into just one core. So after a lot of struggling, we decided to go with the Express Data Path, which is the functionality enabled by the eBPF that Linux supports. And then I have a reference for that. But basically what XDP does is enables you to bypass the Linux networking stack. Because if you have, when we are using the networking stack, we're having 75 to 85% of packet drops because we're not being able to processing that data. And with XDP now we haven't seen like drops so far. But one of the things that XDP is very good is to process that data while the packet is on a NIC or just leaving the NIC, but it doesn't store that data. It doesn't do much of that data if it's not just real-time monitoring. So we realized it's not possible for us to save all those telemetry reports. So Yatish also mentioned this, there's a lot of challenge for you to store all that data in. I'm not talking about disk space, I'm talking about being able to, in one CPU core, to do all the struggle to not just receive, but also push to someone else to write this. And what we decided to do is we decided to only report change or only store the change in the behavior. So if there's a queue that increased or dropped more than 20 kilobytes, or a flow path that changed, the hop delay that increased more than 2 microseconds, or an egress interface that is using more than 80 gigabits per second, then we record. And that data is recorded into InfluxDB. So that result that now we can have close to real-time processing, but we don't have that granular measurement because take a look at this figure in the bottom right side. So you can see that you have those green squares. Those green squares represent, for example, it's just an example of a measurement that we received, like a telemetry report that we received. So we create like upper bound and lower bound, and we only report and we only store in the database one measurement from that interval. So you have those green squares that have a black dashed square surrounding them. And that means, well, that's the first flow from this behavior. So from now on, I'm not going to store, and I'm only going to store when there is a change. That means that we lose granularity, but at least we don't overload our server, because before that, we're not being able to save anything. The next challenge that we have is has been talking about machine learning, AI, and we have been talking to some researchers in this field, and we have heard like this complaint a lot of times. So there's no grounding truth for learning algorithms. There's no grounding truth for networking. So how am I supposed to know what an elephant flow will be if I don't have this kind of data to use, publicly speaking? And just as an example, going back to the Vera Rubin telescope use case, so within those 5 seconds, we have 13.6 gigabyte. That means that at the end of the 5 seconds, we're going to have almost 337 megabytes of telemetry data. There will be 1334 observations a night, meaning that we're going to have at the end of the night or 450 gigabytes of telemetry data. So even if we were able to save all of that, which I don't think we will, or I don't think we need, but who's interested in that and how they are going to download that? Because that leads to a lot of those challenges that all of us are used to, like how do I save, how do I store, where I store, how long should I store, how do I share? Okay. And so is it really need all that information from the telemetry report? Can we just remove some content? And what else do I have to combine with those reports? How do I have to combine with topology information or a more descriptive approach to explain what that data means, for example? So this challenge 3 is wide open. We haven't started that. And we're a very small team. We're looking for collaboration. So if you're interested in this kind of thing, you have suggestions, please let us know. So I want to close with just providing 2 links. This link on the top was a presentation we made in December 2019. It was an hour long. It's part of the ESNet CI Lunch and Learn. So we had the opportunity to talk about our project, introduce to telemetry, introduce to INT. And we have a follow-up to that one on January 22nd. That we're going to talk about the interfaces, the code 2 years later, the demonstration, and then challenge the opportunities for collaborations. So again, thank you for the opportunity, and I hope this was helpful somehow.
Thank you very much, and I apologize for my intrusion during your presentation. Okay, you can now unshare. We can have discussion after the whole session, and I could please, Richard Siva, can you share your presentation and start with it?
Yeah. Hello, everyone. My name is Richard Siva, and I'm a software engineer at ESNet. And I'm going to talk to you about our project called FastKapa, our FastKapa NG, which is our DPDK project to process telemetry data. It's joint work with the high-touch team with Bruce, Yatish, Chin, and others. So as those who don't know, we're ESNet, and we provide a high-performance network for US laboratories, some laboratories in Europe with transatlantic capacity. And we connect also a lot of supercomputers. I would like to first start about the type of network packet data that we collect. The most basic one is SNMP. We pull them from all of our interfaces at every 30 seconds. Most of you have seen our live network visualization, traffic visualization on my.es.net. If you haven't seen, go check that out. That's a really powerful visualization of all of our traffic that uses SNMP. So for that, we are talking about the data rate of approximately 130 events per second. And that's with our 4,000 interfaces that we currently manage. Now, that's SNMP, very low data rates. We also have, of course, NetFlow, as every other provider. We collect 1 to 1,000 sampled NetFlow for primary use of capacity planning, for example. Here, the raw data rate is 50 times higher. It's around 7,000 events per second. Now, this project, where we do per packet telemetry, we call it high-touch services, as Yatish talked about. Here we collect for every single packet a telemetry event. So it's a one-to-one mapping. Here, the data rates are up to the millions. In fact, it's pretty hard to calculate an exact number due to the differences in packet sizes, but we're talking about 1 to 8 million events per second on a 100 gig link. So as you can see, there's a huge increase when you go from a sampled flow data to a per packet monitoring system. Now, the per packet data rates really depend on a couple of factors, and the most important is packet size. So of course, if you have a nicely configured network where most of your packets are jumbo frames, you will have less telemetry packets if you do per packet telemetry on that traffic. If you have a lot of small packets and then you do timestamps on all of these packets and collect all of these packets as individual measurements, it will add up. So we did have a look in different interfaces in our network to see an estimated average packet size. So you can see on a CDF on this slide where we looked at one of our peers with Internet 2. We looked at an LHC1 site as well as 2 core links. So as you can see, I just want to point out, for example, an LHC1 site, which is one of our science domains. The red line here shows that even while this is a jumbo frame configured interface, here the average of the packet size is 1,500 bytes still, like on large. So we are taking this 1,500 byte as the average packet size right now in our network when we calculate ballpark figures of how much telemetry we would get if we would timestamp and create telemetry of all the packets. In this table, you can see on a 100 gig link, if it's fully utilized with and with 1500 byte packets, we're talking about 8 million telemetry packets per sec, and a telemetry rate of around 10 gigabit per sec. Of course, if they would be all jumbo frame, 100 gig link, then this 8 million would go down to 1.3 million. Without spending much detail on this, this is the overall architecture of our telemetry and per packet inspection system. We use FPGAs to get traffic from our routers and do timestamps on them, and then forward them to a collector system. And that collector system is where we run a Mellanox 100 gig card with DPDK and a Kafka to distribute the packets to different applications. We also have the ability to get all the telemetry packets and stream it to a remote location. So if we need additional processing capacity, we can use data centers to spin up more data crunchers. So this talk is more on FastKappa NG, and we have not talked about this before. This is software that we develop internally at ESNet, and it's based on an Apache Metron project, which was called FastKappa. And so we took that one and we developed heavily on that. So we kept the name, and then it became FastKappa NG as next generation. The primary functions for this is to process the telemetry data, listen on an interface, on a DPDK interface, and get all the data, so process it, pre-process it, filter it, create batches of it when you send it to Kafka or write to disk, aggregate it, and so on. So we, for design for this, the most important part, and it's pretty hard to deal with this when you do this, is to preserve packet order. So for all of our telemetry applications, we want to make sure that when they read telemetry data, they are in order as they were in the network. So there's no out of order processing. It's pretty important for example, tracking retransmissions when you rely on the TCP SYN and ACK acknowledgement numbers. It's just easier to implement applications if they don't have to deal with reordering. Now, this whole pipeline is, as we call, a multi-pipeline, multi-stage type of architecture. We can define these so-called pipelines for different set of flows, and the packets in the pipeline will go through multiple stages. Let me talk a little bit about these stages. So first, the telemetry packets arrive on our interface, which is, as I said, a 100 gig Mellanox interface. We use RSS to map from the physical port to different receiver queues. And then the pipelines will pick up, based on configuration, packets from these receiver queues. And first, we have some workers that read from the queue and put packets into the ring buffer. Here we still have the different flows in one ring. Then we have an ACL worker that will filter out flows to different rings. It's an important part here that from this point, the flows will be handled separately with different processes and different rings. The most important part in this whole implementation is the flow workers. These are processes that crunch the data. They are the one that can do sampling for us, histogram generation, filter packets, and all of these, I would call them network functions in some way. When these network functions process packet, they essentially read from a ring and then write to a ring. Once they've done that, there are separate processes that take out the packets from the ring, batch them together here, and send them to Kafka. So altogether, if you look at this, all of these little boxes are DPDK processes, so they take a full CPU core. So even in the minimal configuration, it needs around 5-6 CPU cores just to run FastKappa. And then when you have multiple pipelines and you scale up, you can reach infinite amount of CPU cores. So that's something we need to always look for. As I said, flow workers are an important part of the whole FastKappa. they, as I mentioned before, they take packets out from a ring and write to a ring. You can here see the code for a sampling worker. So that is just a basic implementation. If you would ever add more telemetry processing to FastKappa, this is what we would do. So we would read out packets from a ring, and you get a lot of pointers to these mbuffs. You do something with them. For example, this one is just a for loop going through all of the packets that it got from a ring. It could be, let's say, 500, because it's a queue. It's a badged DQ. It checks. It takes every 10th packet, because or every, like, depending on sampling. Let's say sampling is 1 to 10, and then it enqueues these packets back to a new ring, to the output ring, and the rest will be just dropped, which essentially in DPD keyword means you free the mbuff. So here it's, as you can see, only a couple of lines of code to implement a sampler. Similar way we implemented a histogram generator. So instead of writing every 10th packet to the queue, we create a new packet, which is a histogram packet. And for every, let's say, 2000 packets, we write that one into the queue. So you can completely transform here how you process your packets. We have done a configuration option for FastKappa. You can configure all of these in runtime, what flows you want to run what functions on, what function and what flows. We also have a lot of statistics that we collect from all parts of the pipeline, from NIC port, RX worker, the ACLs, the flow workers. And so we take all of this data, and as well as others, we put it through Prometheus and then just visualize it in Grafana as well. We can see we can always see where the packets are being processed. And in this particular example, it was a 1 to 10 ratio reduction. We can see the packets per sec was 500,000, and then it just became 10 times lower when it wrote data to Kafka. So I want to also talk a little bit about Kafka. If you just run a Kafka, a ballpark figure you can get for message intake is around 5 million packets per sec if you have a very powerful server. And let's say you run a couple of brokers, 4 or 5 brokers, and the parallel producers that write into Kafka. You can see the performance grows until one point, and then a server becomes overloaded. It will quickly drop down to only 2 million packets per sec. That's Kafka messages here. We run Kafka with Docker. We have Bitnami containers, Bitnami Kafka, Zookeeper, JMX exporter for all the statistics, and Prometheus Grafana. So this is important. So around 5 million messages per second you can get for Kafka. Of course, it's not enough. We talked about the 1 to 8 million telemetry messages per sec. In order to push this further, there are a couple of implementation things we are looking at actively. But another very easy way to push this further is to just put more telemetry packets, more telemetry packets into one Kafka message. So this is what's happening here. You can on top of the message batching that our Kafka library does, we can also do packet batching inside the messages. And with that, you can reach up to 20 million. So here we show until 60 million packets per sec, telemetry packets per sec inside being ingested into Kafka. So we utilize this to reach over 10 million packets per sec. Now, Yatish talked about this, so I'm not gonna do anything on this topic. But in very brief, once you use the histograms, you can take the histogram data. You can learn it with machine learning and do TCP congestion control identification. I'm just showing this just to show that we're building heavily on the histogram data format. And that's, again, something we can generate now in FastKappa. The last slide is how you program this. So when you use Kafka, you have this library called Kafka Streams. This gives you a very easy way to do very high-level implementation. Let's say here it's a SYN flood detection. As you can see, takes a stream, it filters out all the telemetry packets that are SYN packets. It groups by destination IP addresses. It can window. I think that's one of the greatest things. It will window, so it will only take the data of the last 5 seconds, and it counts the packets. And if it's over a threshold in the filter, it forwards it to a new stream. So in this presentation, I just showed you a little bit on FastKappa, which is a DPDK Kafka project that we develop. We can execute stateful functions on our telemetry streams, sampling or histogram creation. We can push around 15 million telemetry messages to Kafka with a single server. I also showed you a little bit on the histograms, and when you see the slides, there is also an academic paper on that, how we use the histogram format to do TCP congestion control detection. And I briefly talked about the Kafka Streams, which allows you to do high-level application programming when you use Kafka. And with that, I would like to thank you.
Thank you, Richard. So it was almost perfect on time. Okay, our next speaker is Doug. Doug will talk about NetSage. So I don't see here, in my screen at least. Doug, can you hear me? If you can start sharing the screen and you can start your presentation.
Okay, there we go. It should be shared now.
Yes, perfect.
Okay, well, good morning or afternoon, depending on where you're currently located. My name is Doug Southworth, and I work with International Networks at Indiana University. And also one of my duties there is I work with the NetSage project along with Dan Doyle. So we're just going to give kind of an overview of what NetSage is, the scalability, and kind of just an overall picture of where we're headed with it and how it can be used in different ways than we're currently using it. So NetSage was originally designed to be a way for people to visualize R&E data traffic. A lot of times we are very good at generating data and putting it into databases, but getting it back out in a way that's meaningful and useful for the average user can be a little more difficult. So NetSage was built to give people quick access to R&E data to see what kind of information is being transferred, who their partners are. A lot of times universities and other larger institutions don't really have a good understanding of where traffic is going. They know how much traffic is heading to different places, but they may not know who their partners are. They may not realize that, you know, at the network level that a research project has kicked up, and now they're moving massive amounts of data with somebody on another continent that they don't really have a good networking relationship with, and so they don't understand the performance there. So we wanted to make NetSage a way to be able to visualize those kinds of performance potential issues, or just a way to see who and where your data is going to. So NetSage is able to digest a wide variety of data. Currently, we're using SNMP data. We do use PerfSonar active data as well. We can visualize that. Flow data that is from routers that some of that data comes from international networks. We manage, of course, the near link that goes across the Atlantic and the Transpac link that goes across the Pacific. We grab data from those, but we also grab flow data from a lot of our other partners. Recently, Ampath, Geronimo was able to turn up a whole bunch of different flow data from Ampath and Amlight for us. We are also grabbing data from Hong Kong, Hawaii to LA, all over the place. We're also grabbing TSTAT based data from data archives at NCAR, TAC, NERSC, University of Hawaii, their astrophysics and astronomy. We can digest all of that and create visualizations that show you where and how that data is being used. So this is just a quick map of where we're currently collecting flow data from, at least on an international scale. We also, we'll get into this a little bit more later, but we can scale this down to be just domestic projects. We've even looked at possibly using this as a campus level project. Where's your data going on your campus as opposed to looking at it from an international scope? But currently international links, this is where we're digesting flow data from. So the data ingest pipeline looks a little bit like this. We have the different test points out there, which is kind of a generic term for data aggregation sites, if you will. So we're taking in, again, the SNMP, the flow, the tstat, perf sonar, any of those data sources. Those end up in our data ingest pipeline, along with data from, we were using MaxMind as a GeoIP source. We're now using the Kida database. MaxMind changed a few things, and we recently migrated away and changed how we're doing GeoIP tagging. We also use data from the science registry that we'll touch on here in just a minute. And all that goes into the ingest pipeline. We discard small flows that are less than 10 megabytes. We stitch together long duration flows. We do GeoIP tagging, science registry tagging, and then we de-identify that data down to a class C or a /24. So you can see the institution it's coming from, but maybe not the exact machine. And that level of anonymity makes most of our partners happy. That all gets dumped into the NetSage archive. And then from that, we generate our performance dashboards that come out the other side. So what NetSage really does best is it answers questions that people tend to ask about their networks. We talked on that earlier. Where is my data going? How much data am I transferring? What kind of speeds am I getting? But while those kinds of questions may be easy for network engineers to answer, one of the real strengths of NetSage is the ability to have people who aren't network engineers, your researchers, your teachers, your professors, they can look at this data as well. And it's presented in a very understandable, human readable format that anybody can go into NetSage and look for patterns or see what specific kinds of projects are transferring data. So it's easy access to R&E data for basically anybody out there in the R&E world. So bandwidth, we'll touch a little bit on some of the dashboards. We don't have a lot of time, so I won't go real in depth, but these are just some of the kinds of questions that we try and answer with every dashboard that we make. So we have different visualizations for data by organization, data by country, individual flow data. Every time we develop a visualization, it starts with a question. We want to know, we basically come up with a specific question and then build a dashboard around that. So everything in NetSage is designed to answer something. It wasn't just designed to be a pretty visualization of data. It was done from a mindset of, what is this data? What are we looking for? And how can we best present that? So I picked on GISC a little bit this morning, used some of their recent data. This was a 7-day snapshot from the time I built this presentation, so maybe 3 or 4 days ago. So this just shows top flows, and there's actually more to this dashboard, but I condensed it down to the very top piece of the dashboard, just so you could see it on the slide here. So the dashboards all have data to and from, so there's source and destination. This happens to be the destination side of it. So these are flows that are going from GISC to different organizations. You can see really quickly, you can get a very fast sense of who are my top partners, not just by volume, but who am I doing the fastest transfers with? And then you can start to drill down a little bit deeper into individual flows. So again, this is the same time period. And over that same time period, we can now generate a table that shows us our individual flows between, you can narrow it down between just partners. In this case, again, this is just to absolutely everybody they've talked to that we're collecting data from. But you could say just to the, say, Yale University, you see there in the second line, I want to see just those individual flows, and it will filter this table down into just that information. And one kind of quick preview here of something we've got coming out in our next version of NetSage. It's not currently in production, but we are evaluating it, is detailed flow information. So if you want to dive down even deeper, I'll go back here for a second. This flow right here on the second line with Yale, if you click on the timestamp in the newest version, that's going to give you even more information about that specific individual flow in terms of who's it from, who's it to, ASN. Again, you can see the subnet. It's been anonymized down to a /24, but you at least know the subnet you're dealing with now. And it's also tied into the science registry data that we talked about earlier. I'm going to touch on that in the next slide. But if it's something that we've identified, if it's in the science registry, it will even spit out what science discipline it is, what organization it came from, all of that data as well. So again, a simple way to see where your data is going and who you're sharing it with. So the science registry that I've mentioned a couple times is a project that runs alongside NetSage that is completely voluntary, and it does give us information that is down to a more specific IP address. But again, that's because that's information that has been volunteered by a specific group as opposed to pulled from flow data. This is all manually entered. If you have a specific project you're working on and you want to know what that data looks like and have that data in NetSage, you can get a hold of us and we can tell you how to enter that information and assist in that process so that when you're looking through NetSage, you can see specifically if you've got DTNs or large servers or any kind of information transfer and you want to know where that's going from. If we put that in NetSage or into the science registry, you get better information out of NetSage on the back end. And we're even developing new dashboards that show, as opposed to by organization or by country, we're developing project dashboards that show, I want to see all the data from this specific project, like say maybe the wide project or something along those lines where you've got a specific scientific domain or project that you want to look at. We can now in NetSage show just that information. So some of the infrastructure improvements we've made in fairly recent history, Grafana has in the past couple versions allowed for queries to be shared between panels. So if right now, everything you see in NetSage, every time there's a new panel, that's a query that hits the database. With some of the improvements to Grafana now, we can share those queries. So if you have several panels that need the same information, you can ask that information once to the database instead of hitting it 5 or 6 times. That improves load times and decreases load on the back end of the server. We've also migrated Personar data from TSDS to Elastic using a push as opposed to a pull model. So we have, again, faster data availability. And Elastic's query language is a little more flexible. So it gives us some different opportunities there to present the data differently. A lot of this comes about because of, as we're ingesting more data and we have more things coming in, we need better and faster ways to look at that. So we're always kind of looking for ways to streamline and make it faster so that dashboards don't take a long time to load, especially when you're looking at maybe a year of data or 2 years of data. Those types of queries can take a really long time just because the huge amount of records available. One of the things we're looking at on that front is data rollups, where if you're looking at large time spans of data, maybe 1 year or 2 years or 5 years of data, maybe you don't need the resolution down to individual flows. So maybe we can do something like a data rollup, where if you want to see general usage patterns and general trends over long periods of time, instead of querying all of these records when you're trying to pull that, now maybe you're just pulling data that's down to resolution of a day or a week or a month, depending on how far back you need to go. And that can all be customized. So that's one thing we're investigating to make data visualization a little bit faster. One other thing we've played around with a little bit is grid FTP at NetSage. So there's a disk-to-disk transfer utility that is now a part of PerfSonar. And we played around with a little bit, being able to show grid FTP data in NetSage.
2 minutes.
Thank you. So we developed a quick and dirty test for Supercomputing 19 last year, where we were able to show grid FTP data between ESNet DTNs and visualize and show exactly what that looks like from a Grafana/NetSage standpoint. And this really was less about showing DTN data than it was about showing the kind of the flexibility of the NetSage framework and the ability to kind of rapid prototype. This all got put together very quickly right before SC, and with help from ESNet and Dan Doyle's group at the Global NOC, we were able to put this out there and show that NetSage is really able to digest any information coming into it and give you real actionable information without having to be a top-level network engineer. So some final thoughts as we're getting short on time here. NetSage was built to answer questions for the average user and not just high-level network engineers, but we also wanted those questions and those answers to lead us to new questions. When you see something, we want you to go, huh, I wonder why I'm transferring data with them, or this data should be going from New York to Europe. Why is it coming across the Transpac link on the other side of the United States? We want everything about NetSage to be able to answer questions and cause you to ask new ones. And some of the things that Dan touched on earlier about scalability is we wanted to be able to rapid prototype, to develop visualizations for specific data projects, and to be able to be very, very nimble about making dashboards and visualizations that answer questions for projects that maybe you don't need it permanently. Maybe you need it for one talk. Maybe you only need it for a month or 2 months. But being able to be agile and answer those questions and not have a rigid framework that doesn't allow you to ask questions that you need answers to. So it looks like I am out of time. I'm going to close it up there and I'll stop sharing.
Thank you, Doug. And I want to thank all the speakers, because I mean, you are out of time, but for 10 seconds, that's really nothing. We came to our last presentation today, and this is from Miriam Kiran from ESNet about S-flow monitoring. So I will give floor to Miriam, but I would also like to ask our speakers to remain with us until the end of this session. We have some questions in the chat, so maybe the best moment is after the next presentation to answer to all of them. So Miriam, please, can you start? I'm sorry, we can't hear you. I don't know if you have unmuted yourself.
Okay, sorry, my bad.
Yeah, that's good.
Okay. Okay, good morning, everyone. I am Miriam Kiran. I work as a research scientist at ESNet, also based in California right now. I'm presenting this work, which is kind of like a collaboration between the testbed teams and the Chameleon Cloud team, which is being developed at Argonne National Lab. So we're doing a lot of AI experiments, and we've come across a few hurdles. So we're going to talk about that. So the proposal which we have here is to have S-flow monitoring dashboards for us to have AI-controlled NRENs. So just a bit of a background on me. I am the PI of the Daphne lab, which I've been actively building. So it's based on deep learning and AI for high performance network, with the message that we are building machine learning and deep learning libraries, which can be directly applied to operational network and distributed computing problems. We do have a website, and we have a lot of tools which we've developed for us. Which are available through open source licenses. So please feel free to go in and have a look, and also contact us for questions. So let's come back to the problem. So we see, and we have been discussing here, that there are many different data sources which you can collect across the network. My.es.net, which Richard mentioned, is collecting very real-time SNMP data which you can see how the network is performing. But there are other data sets which you can also collect behind the scenes. So you can do net flow data. This particular picture is of NERSC, and you can actually visualize what the data set looks like based on months to see if there's a certain kind of behavior in the site. But you can also collect persona data, which is a different database. And then there are other teams which collect BRO, TSTAT, and many other data sources, which I might not have included here. SNMP data is actually very good to see where the traffic surges are happening per time, and that can be linked in to see alerts and actually send alerts to engineers to see if something is happening on the network, which was not predicted. So one key takeaway from this is that a lot of these data sources are not connected. So they're all collected at different time zones, time scales, and also at different locations. When we talk about AI, so our group is basically aiming to build this picture on the top over here, where we have the environment, which we are visualizing as the network. And then we have an agent, which is monitoring what is happening on the network and learning how to behave and actually make decisions which are going to be beneficial for the network. So if we now expand that small picture into this big picture, which is at the bottom here, we have a network which we have set up on Chameleon Cloud. So we're doing a lot of our experiments in the actual test beds. So we have Chicago connected to Texas, but you have many different ways in which you could get to Texas. You can go via New York, or you can go via Washington. So our whole idea is to collect all of this kind of different monitoring data, bring it up into a custom dashboard, and then actually feed our deep neural networks to learn from this data, which can then take action on this network. So this is the high level vision which we are building towards here. So in the first phase, we're still building the dashboards to actually feed in our neural networks for this challenge. So we need to get our data right before we start. So when we started this project, we wanted to start with what is actually available on the network and not actually develop any of our own monitoring tools, for example. So this picture right now you can see is basically just showing you 3 different sites: Sunnyvale, LBL, and NERSC. And I've kind of tried to expand how these different devices are installed on those sites and what kind of data is actually collected when we do this. So for example, we can have all of these routers, which are represented by blue boxes over here, which are installed on the sites. You can then install persona hosts on some of the sites, which are represented as red boxes. Now, when we go down and look into what the data is being collected, SNMP data is actually counts of data moving in and out of these interfaces. Then NetFlow data is end-to-end of a complete flow, for example, in this case, moving from LBL to NERSC. And then persona data is actually the end-to-end performance data between the persona hosts and not the actual sites. So this was an interesting thing to investigate, because when you start feeding your AI with the data, you really do have to know what the data represents and what the AI is actually learning. So we started with this initial thing to see where we are. And we started then building our own topology on the Chameleon Cloud and seeing which of these data sets we could bring in. So the way we do this is we experiment with the network layer, where we represent our own VLANs, set up our own VLANs with our networks and nodes. Then we have a lot of these monitoring tools installed to do the data collection and aggregation. And then finally, we do the visualization. When we get this visualization, we could also feed this into the AI thing to actually do the learning and controlling of the network. What we have been doing this year is we've developed this toolkit called Netgraph. So we have the network layer right on the top, which is represented over here. Then we installed all kinds of open source. So we did a search on what kind of open source tools are out there and what kind of data they collect. So we found these 6 open source tools, which we actually put as part of this toolkit. So all of those can then be installed on our nodes, which we have on our test bed. And then based on how those tools work, we actually funneled the data into different kinds of databases, finally into a Grafana dashboard, which can then be connected to our AI controller. So we came across a lot of new interesting findings where some of the tools were very difficult to connect to a Grafana API directly. So we needed some interface dashboards to actually make the data available for that to work with. A little bit of insight into what these tools collect. So the reason why we went with so many different tools is because they all collect different kinds of data sets. So NetData was collecting syslogs, TCP data. Prometheus was collecting node level data, but we were more interested in network data. We found Zabbix and Qtop NG, which were also collecting different other kinds of data sets from different parts of the network. And then finally, Profsonar, which collects throughput, loss, and latency. So the key highlight here is that different monitoring tools are collecting different kinds of data sets. And if we want a complete picture of the network, we do need to come up with some way in which we can synthesize all of this information into one. Grafana was only being used as a GUI here, and other databases were being used just to collect data. This is the end result of what we got. We now have a custom Netgraph dashboard, which is an all-in-one dashboard. So the idea which I had behind this was kind of like a car dashboard where you can just look at the car dashboard and get a picture of what is going on in the car. So that was basically the image we were going for over here, where we have all of the different nodes installed on the network. And in one shot, you could see everything, all of those monitoring data being filtered into this dashboard. Now, this was very good. We were very satisfied with this. But what we realized was that in order for the AI to use this, there was a lot of noise in this data. So we then went back to the team within the testbed teams, and then we had another set of discussions on what would be the best way to go forward with this. So this is where the testbed engineers and everybody has now reached an agreement that we need to go towards SFlow as a better monitoring tool rather than the open source monitoring tools, which we were experimenting with the Netgraph. Mainly because we need very clean data sets to train our AI with. The way we're doing this is that Chameleon has a service called Security Onion node, which is also known as a security method otherwise. But basically what they're doing is they're trying to mirror traffic from one network device into another node, which would mirror SFlow data going into that. And this way we could collect data at the network layer, at the host layer, virtual layer, etc. And if we are able to do this, we can basically replace all the 6 monitoring tools which we were doing before with just SFlow enabled devices. So this is the overall picture which we're going towards, that all of those SFlow agents would then be copying data into a separate node, which would have all of the monitoring data being hosted. And then we can very easily build a visualization dashboard, most probably just using Grafana to see the whole picture of the network. So this work is what we are doing now. So we are setting up SFlow agents on the test bed in order to allow our AI controller to work with this. Our AI controller is called Deeproot. We have an initial version of it already published, which I could also send some code if people are interested in. Netgraph, the toolkit itself, is also available to the community, which includes all of these 6 different open source monitoring tools which we were working with. One reason for doing this is because we are particularly aiming the researchers who are developing network test sets on their test beds, and they just need some quick monitoring tools. They don't need lavish engineering toolkits, for example, to see how this is working. So this is ready to download, and one of my postdocs is currently adding Ansible to this so that it can be easily hooked into any other test bed and can be given to anybody who wants to deploy this on their system. However, we do want to go towards replacing all of those monitoring tools with SFlow monitoring because this will lead to a better real-time monitoring data set, which is much more reliable to play with. As another outreach of our particular group, we are also doing a lot of other monitoring tools such as DTN to DTN tests. And I'm also making a lot of my machine learning libraries, such as deep learning libraries, open source for using with network data. And my group is trying to reach outside ESNet and also work with other network organizations to see if we could actually let our tools work with some of the data sets which you guys have. So we are interested in collaboration and discussions, and feel free to reach out to us. Netgraph is also published and available for download. It's being presented at Supercomputing this year. So hopefully we get some interesting discussions from all of you here. And with that, this is our website for more information and downloads. And please feel free to reach out to us if you have any questions.
Thank you, Miriam, and thank you all. Well, this is the end of this part of the workshop where we have the presentations. There was a bit of chat while we had those previous presentations. So, Damian, you asked a couple of questions. Are you happy with those? Or would you like to ask something else, or is there anything else that we could discuss in that area? And then we'll go next, Professor Maglaris and so on.
Okay, I received, let's say, responses to all my questions. So currently not needed to go here.
Okay, thanks. So Professor Maglaris, would you like to ask the question? Because I'm not sure to whom this question is asked. Or this was to Miriam,
this is
I guess.
A question to the last speaker, and you know, she said that she would use data from SFlow and so forth. And my question has to do with sampling in SFlow and whether this sampling might hide some of the dynamic features that are inherent in the networking traffic.
So we have been experimenting with this. So a lot of the data which we are currently building our machine learning around is also sample data sets. So that includes SNMP and NetFlow data. So those are also sample data sets. In terms of whether it hides dynamicity, for our particular problems, it doesn't, because basically what it does is our machine learning works on intervals. So every 5 minutes, it takes a sample and then it makes a decision. So basically the way our machine learning works is that everything is compounded into that 5 minutes. So even if there is erratic change, which has happened in 5 minutes, that 5 minutes would include all of that major peaks. So your machine learning would make a decision based on what it sees in that compounded data at that 5 minute interval.
Okay, thank you.
Thank you. Mauro? You have a question.
My question was, how fragile is the AI model that you're developing? You partially answered because I was thinking about how fast the network traffic changes and how unpredictable sometimes it is, especially for the research and education like this video conference of 100 members all of a sudden in one place.
Mm-hmm. So the way we've done it is that we've had a lot of discussions with the engineers to see what they want the AI to actually do. One of the use cases has been that, can the AI predict that this is an elephant flow versus a mice flow? And if it's an elephant flow, put it on this path. So in that particular situation, it's not, so the fragility is not so bad because you're basically just using it as a flow recognizer in that sense. The other part, which is the traffic engineering one, which is the example which I was giving here, we are working in time intervals again to actually, because the network is so fast. Richard did this talk to show how fast the network is. Right now, we don't think we are going to go to those levels. We just want the basic things to work, like even at 5 minute intervals, and just actually show that the traffic engineering would be improved with an AI controller. And then once we achieve that step, then we will start talking to Richard's group and seeing how high touch data could actually improve the intervals which we are working with. But we need to get to the first point first. Thank you.
Thank you. Do we have any other question from the audience or from the speakers? Well, I guess
if not, I could
Tim,
present
please.
the part 2 of the Mentimeter. Just a moment.
While team is preparing, I think that this talk on AI at the end actually is a very nice closure of the discussion that started from technology at the fiber level and then goes up to AI. And I think the more I think about the presentations, the more I think the same things. Everything is really related one to each other. It's much more difficult to decouple the things.
All right, here we go. Sorry about that. You're getting a... Oh.
So we should open a browser.
Right. That's not the right one. Hang on.
To participate to this Mentimeter, please choose a browser, go to menti.com, and then Tim will tell us a code that you have to input in the window. The code is shown there. Please go to menti.com and enter that numeric code on the top.
So that was a screen showing you a mail list that you can join, which we'll show you later. Here's the questions for the second Menti slot. The first one is coming back to what was presented around sharing data. So if you go to menti.com, put in the code, it's a different one this time, 881836, and then give us an indication of whether you are sharing your data, particularly obviously if you're an operator of a network. And if you are sharing it, with whom. You can tick multiple boxes there in this one. So again, there's 80 odd people connected, so we'll give a little bit of time for you to put things in. So it's quite a surprising, well, to me, that seems like quite a surprisingly high number sharing with network researchers, which is encouraging. There's certainly a majority that are at least an equal amount, a slight majority that are sharing their data. So we'll move on. It might be that there's only 35 people responding because there aren't that many NREN operators here. So yeah, it's fairly even between sharing and not sharing. And for those that are sharing, it's both to other operators and researchers and a handful of other use cases. So a little question here, if you are sharing data or plan to share it, what do you expect the benefits or the use cases you would apply that to? I mean, we heard a few ideas from Alex's talk earlier, but are there specific use cases? Those of you that are sharing it, are there specific use cases in mind or benefits you're seeing from it? That's helping researchers, obviously a good and fairly obvious answer. A few people saying end-to-end analysis, multi-domain analysis, that kind of makes sense. End-to-end visibility, increasing collaboration, helping to understand what the data means. I mean, that's a good one if you're bringing in disparate data sources. Learning things about our network that we didn't expect, that's a good one. Speeding up troubleshooting, engagement with science. Okay, I'll leave this up for a few more seconds and then move on to the next question. Collaborative anomaly detection, another good one. Okay, we'll move on. For those that maybe aren't sharing their data, I was expecting a lower number for the first question. For those that aren't, would you consider doing it? And if so, to whom? So it'll be interesting here if the number of people saying no is quite low. That would imply those that aren't sharing it are kind of willing to do so, but just haven't found a way to do it yet, or have some concerns about doing it. Okay, so that's a fairly even split again, as the first question, fairly even between other operators and network researchers. It seems those that are sharing are happy to share to both of those communities, and again, a handful of other use cases. So coming back to why no, none of the above is 0, which is very interesting. It implies everyone is, and this is going to be a late click on that, everyone is willing to do it. The next question is, what are the issues you'll foresee with sharing network monitoring data? So this kind of is angling at, for those of you not sharing it, those 15 or 20, whatever it is in the first question we asked you, what are the reasons for doing it? I mean, the privacy and GDPR are a couple of ones you'd expect to see here, and seeing it quite a lot. Yes, a lot of privacies, a lot of GDPRs. Are there other issues? Is it, I say purely because it's potentially a complex issue, is it down to the privacy and GDPR and safe release of data? Is there anything else there that's perhaps a more technical issue rather than a GDPR or privacy issue? No, it's all GDPR. I've never seen GDPR occur so many times on one slide before. It's okay. I think the message is fairly clear there. A handful of little technical points coming up as well, which is interesting to see. I think if the GDPR issues people have can be resolved, then obviously those technical issues come a little bit more to the fore. All right, thank you very much. So moving on to perhaps a slightly more positive question again next. For those doing network data analytics, and we heard some good examples today, NetSage, etc. What sort of data sources would you be interested in drawing on for those analytics? We saw, for example, with NetSage, that was drawing on TSTAT, Sonar, NetFlow, and SNMP as an example through their measurement points. What do you think would be good sources for you if you were doing this? All of the above. Okay, perhaps we'll just leave it there. QDEPs is a good one. Buffer sizes and QDEPs. So this again is a word cloud. So the most common answers will be in the largest font. So perhaps unsurprisingly, NetFlow and related friends are the biggest ones there. But QDEPs is quite coming up a bit. Int. Okay, again, thank you very much. And move on to the penultimate question. So the last couple of questions are about what we might do next. So the first question is more for you and your own organization, from today and what you've heard, and maybe other ideas you already have. What technologies are you most keen to explore further for your own organization after today's workshop? Are there specific things that are next for you to investigate further with a view to adopting and deploying? Anything specific you want to say here? Again, you can put in as many answers as you like here. Okay, streaming telemetry and int quite large. DBDK. So Grafana for visualization is quite common. Int is front and center as well. So that's interesting. Int is obviously in its relative infancy, but offers a lot of potential. So yeah, it's the topics from this morning's session of streaming telemetry and int that are focusing there, but there are many other things appearing around machine learning, visualizations, InfluxDB, people that want to go and look more about NetSage. That's all interesting. And the final question, since we're here as a community of largely, it's both GÉANT and the rest of the world, NRENs and other operators, network researchers, what do you think is the final question? What do you think are priorities that we should work on together as a community if we're going to collaborate on ideas, work on things? Do you have different answers here to the priorities that you have for your own organization? Are there things that you think as a community, by working together, we can do better? Things we can take forward from today? So sharing is coming up a lot. Standardization of data and maybe the data formats that we're using. It's a good topic. Sharing expertise. Yeah, there's a lot of information sharing, obviously working on that. addressing those GDPR issues, no doubt. Okay, I'll leave this up just a little while longer in case people want to contribute more in here. Again, we'll, as with the first Menti, we'll turn the answers into a PDF and share it via the event page in due course. Yeah, a lot of data sharing. Common APIs and data formats obviously will be important if we are going to share the data. Another good point there, focusing on the things that we can do as an R&E community that the purely commercial operators can't do. That's important for us. Okay, thank you very much. I think I'll leave it here and hand it back to, I think Mauro was driving things. So again, thank you very much. We'll publish these as soon as we can. I'll stop sharing now and hand back to Mauro.
Yeah, actually, the last shares
Some very interesting answers there. Thank you.
I can't but say a big thank to everyone. I think that this is the most useful comment from me, actually, far from being technical. I think that this workshop, which was organized honestly by a limited number of people and grew in just a few weeks, actually demonstrates the capabilities that our community has and how much is important that they continue to speak one to each other. And I also think that we identified well how our network are evolving from the old model. I can't say old model because I saw the old model, I actually did the old model, and what we have witnessed today is a different way of doing networking. Although the network stays the same, it's all completely in our purpose and capability to change the network, then the tools and what we want to learn from the network has evolved greatly. So thanks again. I think we still have few minutes for any question or any comment from any of the participants. So I will leave the floor to any participants if they have questions or any comment.
Lars did have a comment in the chat. Lars, do you want to say something out loud? Or?
Lars,
no, that was just a comment to the Mentimeter that was going on at the time.
Okay. So while we are waiting for anyone for more comments or questions, Tim, can you please bring up the slide with our future events? So just to announce. Yes.
So I have a comment. Well, first, it was a great conference for me. This is Geronimo speaking from FIU. One of the things that I think eventually would be good for us to start talking is, I don't have an answer, it's more like to poke this conversation, is that the footprint that we're seeing, how is it changing from the perspective that our networking devices are getting a lot smaller and our monitoring devices is getting a lot bigger. So we are moving towards those P4 platforms. And we're seeing that now we have 1 or 2 rack units per rack. And now we have 6, 7, 8 rack units of servers to be able to collect and store the telemetry. The amount of disk, the amount of power that the monitoring side that used to be 1 or 2 rack units is consuming is growing exponentially, even though the devices are getting a lot smaller. So one of the things that we keep thinking about is how do you create a balance between, because more granularity or more accuracy that you have, it means that you need more networking or more computing resources to store that. But in the end, that's just to store data that is to support the network operation. And a lot of us have a lot of restrictions in regard co-location in some sites. So I have sites that have no space for more servers anymore. And I'm not gonna add more power circuits or more co-locations just because I need more power to monitor INT, because INT is not my goal, it's not my business. My business is to forward packets. Of course, INT helps a lot, but I also have to find a balance between budget and operational costs. So this is one of the things I'd like to see us talking in the future, is this, what is the idea? Should we buy switches and then buy a mainframe with those switches to monitor those switches? Or what's gonna be a future of this?
I think it's a very good question, Geronimo. My point is that there is not just monitoring hardware. What I'm a little bit worried about is the amount of software we start to introduce in our network for a lot of reasons. We need expertise, security, and capability to maintain the software for a longer period of time than just a few years. So I think this is one of the key political and strategical decisions that we will have to make. And obviously, it's on the interest of everyone to converge to the same time of decisions. From my point of view, I think that still the data is what will drive our networking in the next years. That's my personal opinion, because more and more decisions will be based on the data analysis. And so I think that, yes, our controllers will be smaller, but I think that at the same time, the integration of chips may actually save space, save energy, and maintain the same quality.
Sorry, just to quickly jump in so I can turn off the slide sharing. Just one slide here, just showing you, particularly for those in the GÉANT community, but everyone's welcome to them wherever you are, obviously, depending on your time zones. You can see all the upcoming events on the GÉANT calendar at the events.géant.org, which is the new event site, as opposed to Event R, which was the old one. We've got 4 events coming up from our own work package. The quantum one's in its very early stages of planning, but that will be around quantum computing, quantum key distribution. If you want to follow up discussions here, we've set up a mail list, Telemetry Discuss, and there's all, I think probably quite a few of you are on the NRENs Slack workspace. There's a channel there, Telemetry, as well for you to follow up. We'll put this information in the follow-up email that you'll get probably later in the week once the recordings are up. So you'll get a link to the recordings, and obviously you know where the presentations are. They're on the event page. And if you want to join the mail list and or the Slack server, you're very welcome. So I'll stop sharing now and hand back. Thank you.
Thanks, Tim. Olaf, you had raised your hand.
Yes. I just want to say that I think this seminar was very relevant to me. So most of the talks really had information elements on stuff that I was working on. So big thanks to the program committee or the people volunteering to talk. And because we are also working on something in UNET called Monitoring 2.0. It means that the way we're doing monitoring is changing now. And I saw some of the talks were talking about how to reduce data, how to get the data volume down closer to the source. And we really can't process all the details in one go anymore. So we need to aggregate and find events and do more sophisticated alarm generation in our network. So yeah, this gave me a lot of food for future work. Thank you.
Thank you, Olaf.
Thank you, Olaf. During the Mentimeter, there was one of the questions if you are considering other use cases for data sharing. Is there anyone from the participants who would like to share some other use cases that were not covered by the Mentimeter?
Well, one group of receivers of data that wasn't explicitly mentioned is our customers, like the universities. And I don't know, Switch, it has been a come and go of attempts to be more transparent to users, but there's also always been some resistance. But in general, I think it's considered as a positive thing to open up our internals to our own customers. Also, I think about commercial ISPs where there's some informal sort of sharing mechanisms when you run Atlas probes or something in the right community, or looking glasses. In effect, you're sharing data with the world, and mostly for the benefit of other ISPs who may be outside of the NREN community. So it's certainly happening.
So Simon, that's a very good point, and it's worth noting that there are some of the communities of users that we serve that are working on this, right? That are building their own sort of domain-specific instrumentation that includes not just the network, but also their, higher levels of the stack, so they can really instrument the entire workflows or whatever they're doing there. And the HEPIX community currently have a working group that is looking into packet marking. So they're trying to develop standards for marking packets with science domains and stuff like that. So that is something we might want to look into with our tools going forward, right? We might be able to see that this much of the data is climate science or genomics or whatever it is, right? And clearly from the sciences and from particularly some of the data centers that are interfacing the networks, there seems to be quite an interest in having that available, so they know all the, the insane amount of data that are coming towards them, how much, the science domains that comes from. So that might be something we have to look into going forward.
Here in Brazil, we are starting to have special clients connecting with our network, like the biggest oil company in the country, which has a lot of many projects for using HPC centers from universities and other institutions. So they work on geophysical research, and we are working like science engagement and performance engineering to troubleshoot their data transfers for the institutions which are connected to the academic network. So they are a private company, but they are conducting some research that's shared with the academic community, and then we plan to share some network data and performance with them.
So thank you all very, very much. Thanks to all the presenters for really being very, very cooperative, extremely cooperative on sending slides, preparing everything we asked for, keeping the time, but most of all for very, very interesting topics. And it was really a pleasure also to have all of you today. We had more than 110 participants during the day, so it was really, really great to have you all here. So closing words from Mauro.
Closing words. The first one that came to my mind is stay safe, of course, in this period. I'm talking from a red zone in Italy, so please stay safe. But thanks again to everyone, and I really hope, and I think I will try to keep in touch as soon as possible. Thanks a lot.